Hi, I'm Brett Maurer of the University of Washington, and I'm excited to tell you about our research on an AI-driven seismic ground failure model. What we're trying to predict in this research is this: soil liquefaction. It's a common cause of damage to infrastructure during earthquakes, and it wreaks havoc on transportation mobility. It turns cities from this into this, and from this into this. If we zoom in, it impacts all types of infrastructure: roads, bridges, lifelines, ports, and just about anything that sits on the ground surface. The end result looks something like this. It's clear that reliable predictions of liquefaction are needed, both prior to an earthquake occurring for mitigation and planning, but also immediately after for response and recovery. So ideally, we could make these predictions rapidly, say within minutes of an earthquake occurring, once the regional patterns of ground motions are known, at high resolution, consistent with the scale of individual assets, and over the regional extents that are impacted by big earthquakes. So let me show you how we do that. Oh, right. There's just one problem, which is that state-of-practice models for predicting liquefaction require costly geotechnical tests, such as the data from a cone penetration test, or CPT. These tests are sophisticated. The models based on them work well, but they're also very expensive, and they result in a data point at just one location. This means it's almost infeasible to predict liquefaction at regional scale using one of these tests. Our solution is to use machine and deep learning to develop models that predict below-ground geotechnical data, which is expensive, using above-ground geospatial information, which is free, available everywhere, and obtained from satellite sensing. The idea is to predict what is below ground using information from above ground. To develop a pilot model, we used a training set of 2,000 nationally distributed CPTs. These are locations where subsurface conditions are known. Our predictor variables consisted of 11 parameters obtained from satellite sensing and existing maps. These are parameters like the distance to a river or coastline, the annual precipitation, or the expected depth to bedrock. Each parameter has a loose correlation to subsurface conditions. In aggregate, they can produce an effective model by way of the machine and deep learning algorithms. The models we've developed have been shown to be efficient on multiple US earthquakes, achieving prediction efficiencies in excess of 90%. Coming soon is Windows software, wherein the models we've developed will be embedded and allow users to predict liquefaction at regional scale in a matter of seconds. If you have questions or comments, we'd love to hear from you. Thanks for listening.